Greetings, calculus class. I'm sorry I'm not here today, but your learning must continue. So, therefore, today we're going to learn about Taylor polynomials. These are really, really, really cool polynomials, by the way, and you will revisit them in your unit on series in a couple months. So this is a topic that will come back full force, but it is considered to be an application of derivatives because how we create the polynomials depends greatly on derivatives. So we are going to develop, the basic essence is, given a transcendental function, such as cosine of x, or e to the x, or even 1 over x, just a function that transcends a normal polynomial, we are going to build a polynomial which models those transcendental functions in the vicinity of a point. For example, if we were to look at the cosine curve, perhaps we would want to say, well, what's a polynomial that models this function around x equals 0? And you'll see the building in just a minute, but the very first thing that we'd want, if we were building a polynomial around x equals 0, is we'd want function agreement at the point, which should be 1 for the cosine function. What would be next? After we had function agreement, what else would we want to agree there? What do you think, Will? Is he right, Jordan? This is weird, recording to an empty room. I'm not used to talking to empty desks. But I'm not talking to empty desks because you're listening to this lesson. So I'm actually talking to you. I'm seeing ghost images of my students before me. Austin, what do you think? The slope? Yes, in fact, we would want the slope to agree there. And then what would we want? So we've got the function agreement at the point. We'd want the slope to agree at the point. And then what? What do you think, Maddie? Don't laugh, just answer. Yes, we'd want concavity to also agree. And then we'd also want maybe the rate of change of concavity to agree, and so on and so on and so on. So here's a little brief history about the Taylor polynomial. I'll give you a minute to read that. Kind of an interesting background of Brooke Taylor. So pretty interesting, the naming of these polynomials. And we will see very soon the Maclaurin name used as a special, one special Taylor polynomial. Actually, anytime the point of interest is x equals 0, then we'll be talking about a Maclaurin polynomial. So any polynomials that we're centering around the point x equals 0 will be called Maclaurin polynomials. All right, so here we go. Okay. We have in the past talked about approximating derivatives. Take a moment and think, how do we approximate derivatives? Emily, what do you think? Yeah, a slope of a secant line between 2 points. No limit. on that slope of a secant point. But just, yeah, two close points, you actually find the slope between them approximates the derivative. And how do we find, or approximate, sorry, how do we approximate the value of a definite integral? Melissa. Don't laugh. So a Riemann sum. Take a finite number of rectangles and either inscribe them or circumscribe them underneath the curve or between the curve and the x-axis and find the net area. Yeah, well now we're going to actually approximate functions through the use of what's called Taylor polynomial. So we start off, we must have actually an infinitely differentiable function in order to do this. And it's defined over an interval containing the point A, and that's going to be the center point of our polynomial. We want to find a polynomial, and it says of varying degrees n. So we can find a second degree, or a third degree, or a fourth degree, or fifth degree, etc., which best approximate f. Okay, the curve fits best in that interval. So here's what the polynomial will look like. This is alpha sub 0. That's your constant term. Plus alpha sub 1 times x minus a. That's your x term. So this is the linear term. Plus alpha sub 2 x minus a quantity squared. The polynomial is written backwards, of course, because, who knows where we're going to end it. All the way up to alpha sub n times x minus a to the n. Okay, this approximating polynomial is actually called the Taylor polynomial of degree n. Okay, of degree n. So we stop that where whatever degree is prescribed. So right now, we're going to develop the general polynomial based on a few things that I just mentioned. So we want to determine the alphas. Once we have the alphas, we have the general form for the polynomial. That can be applied to all sorts of different functions. So the very first idea is we want the polynomial function values to agree at x equals a. Okay, because otherwise the polynomial and the function, sort of kind of like that cosine curve that I was talking about, we want them both to be 1 right there. Okay, so really what we want is we want p sub n of a to equal f of a. Okay, we want p sub n of a to equal f of a. Now, what is p sub n of a? Well, if we put a into this polynomial up here, this one right here, okay, if we put a into that, p sub n of a is going to equal alpha dot, because all of those terms, these terms right here, all of those are going to zero out if we stick a into our polynomial. So therefore, alpha naught will equal f of a. Okay? Alpha naught equals f of a. Well, all we need to do now is find all of those other terms. Let me erase some of this so that it's clear. Okay? Now the second thing, if I put it on the next slide, let's see. Oh, there it is. Yes, we have the fact that alpha naught equals f of a. So how would we like our polynomial and function to agree? we want the function values to be equal. Okay. Secondly, the second characteristic that we would like our polynomial to have, the function also has around the point A, we would like the slopes of the tangent lines to A, f of A, to be equal or the same on both the polynomial and the original on F. On both the polynomial on F. Okay, I'm going to turn the speaker off for a second here. It's giving me a little grief. Okay, so that is, we want the nth degree polynomial at A, we want it to equal f prime of A. Okay? So what we have to find is what is that nth, or excuse me, the first derivative of the nth degree polynomial at A. Okay, so we know p sub n of x is equal to, the alpha naught drops out. The next one becomes alpha sub 1 plus 2 alpha sub 2 times x minus a plus 3 alpha sub 3 times x minus a squared plus 4 alpha sub 4 times x minus a cubed, and so on. So, oh, excuse me, that's the derivative. I meant to label that as the first derivative of p sub n of x. So the first derivative of the nth degree polynomial at A is equal to alpha sub 1. Because if I put in A here and A here again, all of these remaining terms will drop. So therefore, alpha sub 1 is equal to f prime of A, because that's what I wanted. I wanted the first derivative of the polynomial at A to equal the first derivative of the function at A, so they have the same slopes. So thus far we have the nth degree Taylor polynomial at x is equal to the function at A plus the derivative of the function at A times x minus a plus some things yet to be found out. But look at this. This is really kind of cool, because this is just, well, look at it just for a minute. See if you can make any conclusions as to what we're looking at here. You got it yet? I hope someone is thinking or saying to the class, wow, this thing looks like a line. It looks like a point slope form of the equation of a line. Here's the y value, right? Okay, here's the change in x over here, and here's the slope, right? So that's really just the equation of the tangent line to the function f. So, you know, we're gradually building this, and what happens in a few minutes is going to depend on concavity, right? Okay, so that is just really kind of cool. So the first two terms are basically building the tangent line to the function. Step 3. yes, another characteristic that we would like our polynomial to have in common with a function is the same concavity. Okay? So we want the second derivatives to agree. Okay? So we want the second derivative of the nth degree polynomial at a. We would like that to be equal to the second derivative of our function at a. Now, make a guess here. What you think f double prime, or excuse me, what you think, I guess we're looking for now alpha sub 2, right? What do you think alpha sub 2 will be? If you said alpha sub 2 is f double prime of a, you'll have to wait a minute and see. All right, so now we need what the second derivative is. Oops, at x first, then we'll evaluate it at a. Okay, this is where I could use the other screen. Let's see. Back to this. Split the screen. There is my first derivative right here. Right there. Okay, so the second derivative is going to equal, okay, this term alpha sub 1 zaps that. I will have 2 alpha sub 2 plus, okay, because that's the x term. So I'm just differentiating that first derivative, plus 6 alpha sub 3 times x minus a plus 12 alpha sub 4 times x minus a squared plus and so on. Because I don't need to go any farther, because what I'm really interested in is the second derivative of the nth degree Taylor polynomial at a. And that is equal to 2 alpha sub 2, because all of those other terms, again, zero out. So therefore, if the second derivative of the nth degree Taylor polynomial at a is 2 alpha sub 2, and we want it to be f double prime of a, 2 alpha sub 2 must equal f double prime at a, and therefore alpha sub 2 is f double prime at a all over 2. So it wasn't necessarily what you suspected. Our whole polynomial now, let's see, back to the full screen. The whole polynomial then is, oh, sorry about that. So far, we have p sub n of x is equal to f of a plus f prime of a times x minus a. That's easy enough to remember, that's the line, plus f double prime of a times x minus a squared, and this is over 2. What the next term is? Well, we're going to have to find out. So this one says agreement at the point. This one says agreement with slope. This one says agreement with concavity. And the next one is really the rate of change of concavity. All right, so the other ones. I think this one will be conclusive. Now, what we want, I'll put this up here. We would like the rate of change of f double prime to agree with that of p double prime at x equals a. So basically, we want the third derivatives to agree. Okay? All right, so we need to take the third derivative. look at the past screen and we say, okay, the third derivative of x is equal to, well, that first term, this bad boy drops, and we get 6 alpha, oh, I bet you're seeing it already, 6 alpha sub 3, that term, the derivative of that term is only 6 alpha sub 3, plus, oh, now we take 2 times that, 24 alpha sub 4 times x minus a, plus, okay, and so on. We don't need to do any of that because we know we're interested in finding p sub n triple prime at a, which is now 6 alpha sub 3. And therefore, since we wanted p triple prime at a to equal f triple prime at a, f triple prime at a must equal 6 alpha sub 3. So therefore, alpha sub 3 is equal to f triple prime at a over 6. What is another way, though, to write 6, which might be more meaningful? Look back here. How was that 6 created? Well, maybe go back even one more slide here. That 6 came from that 3 times that 2, right? That 3 times that 2. So the next one, I mean, another way of writing that 6 is 3 times 2 times 1, or 3 factorial, right? So actually, the 2 from the alpha sub 2 here, this one right here, could be written as 2 factorial. Therefore, the final Taylor polynomial can be written the final Taylor polynomial. Oops, another wrong page here. Uh-oh. Stop that. I don't want this. There we go. I added a few funky features. The final Taylor polynomial can be written as p sub n of x is equal to, and this is a Taylor polynomial of degree n, Taylor polynomial of degree n in the vicinity of x equals a is equal to the function at a plus the first derivative at a of the function times x minus a plus the second derivative at a over 2 factorial times x minus a squared plus the third derivative of f. Make sure that's clear. The third derivative of f at a times x minus a to the third over 3 factorial plus the nth derivative of f at a over n factorial times x minus a to the nth. And yeah, you could actually go back here to these early terms and say, well, that's just like that divided by 1 factorial. This is just like dividing by 0 factorial, because 0 factorial, of course, we know equals. That is the form of the Taylor polynomial of degree n, which approximates transcendental functions in the vicinity of x equals a. Okay, so let's do an example, and then we'll see what the heck does this really mean. Determine the Taylor polynomial of degree 4 that approximates the cosine of x around x equals pi over 4. So yeah, you're going to have to know some of your trig values. So now the Taylor polynomial of degree 4, I like to write out the terms, is equal to f of a, get some practice, plus f prime at a times x minus a, plus f double prime at a times x minus a squared over 2 factorial, plus f triple prime at a times x minus a cubed over 3 factorial. Make sure you're writing this down, Nick. Plus the fourth derivative of f at a over 4 factorial times x minus a to the fourth. So I don't think these notes are going to be posted. It's too big a file. Okay, so there's the fourth degree Taylor polynomial that approximates cosine. Well, that's the fourth degree Taylor polynomial generally around a. So a, in this particular problem, the point at which we're approximating around is equal to pi over 4. Okay, so everywhere you see an a, we know we're going to have pi over 4. So now the next thing we need to do is identify the first, second, third, and fourth derivatives of cosine. Okay, so f is cosine of x, f prime is negative sine of x, f double prime is negative cosine of x, f triple prime is back to sine of x, and the fourth derivative is cosine of x. Now at pi over 4. Please tell me you remember your trig values. Pi over 4 is this lovely one right here. So it's the one where the x and pi are equal. So cosine of pi over 4 is going to be root 2 over 2. Negative sine is negative root 2 over 2. Negative cosine, negative root 2 over 2. Sine is root 2 over 2. And cosine is root 2 over 2. Okay, so the final polynomial then, and for now we can write it without simplifying it. Don't look shocked, Mr. Young. F of a, the function at a is root 2 over 2 plus the derivative at a, I guess that would be minus root 2 over 2 times x minus pi over 4. Okay. Plus the second derivative at f over 2 factorial. So the second derivative is negative root 2 over 2. So another negative root 2 over 2 over 2 factorial. X minus pi over 4 squared. And then the next term should be the third derivative plus square root of 2 over 3 factorial. X minus pi over 4 cubed. And then the last term is plus root 2 over 2 over 4 factorial times x minus pi over 4 to the 4. Okay? A polynomial. The numbers are ugly, right, but it's still a polynomial. We still have powers of x. And so this function would model the cosine function nicely in the vicinity of x equals pi over 4. And in a minute I will try to verify that, but I don't want to plug all those numbers in at the moment. Actually, that shouldn't be too hard. No, it shouldn't. I will just let root 2 over 2 equal something here. Okay, I'm looking at my handy dandy PI84. I'm going to clear out what I have there, and I'm just going to go, let's see, square root key, second square root of 2 divided by 2 enter. I'm going to store that in for alpha a. Okay. So now I'm going to go into y equals, and I'm going to say alpha a minus alpha a times, I should store pi over 4 in for b. Yeah, that would make life a little better. Okay. So second pi divided by 4. Enter, store that in for alpha b. Okay, good. And go back to y equals. Okay. So root 2 over 2 minus root 2 over 2 times x minus alpha b minus alpha a divided by 2 times x minus alpha b squared, right? Yep. Okay. Is that right? Got the linear? I got the quadratic. Good. Okay, plus alpha a divided, well, let's see, let's go back and put parentheses. I don't like that. Alpha a divided by 6, save it. There is a fancy shortcut key on your TI-89 for factorials. I'll have to remember what it is. It might be something like diamond bar or something. I'll have to look. A over 6 times x minus alpha b raised to the third, okay, and then plus parentheses alpha a, oops, parentheses alpha a divided by 4 times 3 times 2 is 24, parentheses x minus alpha b raised to the fourth. Okay, so that's the Taylor polynomial that we think approximates the function cosine of x in the vicinity of pi over 4. So I'm going to go from 0 to pi over 2. Whoops. Okay. 0 to pi over 2, so halfway through there, scale it by pi over 4. Okay, and we only need to go down to negative 1, so I'll just go negative 2 to 2, scale it by 1s. Okay, now let's look at the cosine curve first. I'll turn that off. Graph, here's the cosine curve. Oh, what's wrong? I'm glad I didn't graph that thing. I shared this calculator with the Algebra 2 students. Oh, I am. Oh, yeah. Okay, it's cosine. I was thinking sine for some reason. Okay, so let's change our window to be a little bit more friendly. Let's go to pi. Okay, yeah. Okay. And now I will add in what we think approximates right around pi over 4. Because they're so close. They are so close. Can you see that? I'm going to look out a little bit. I want to go from negative 2 pi to 2 pi. There's my cosine curve. Oh, no, there's my polynomial. Yeah, that's a 4th degree polynomial. That's what it looks like over a larger domain. And here comes the cosine curve. Yes. Okay, take a look at that, folks. Is that not just really, really cool? Because what we can see is right in the neighborhood of pi over 4, which is right in here. Okay, we can't even see how the functions are different. So we see actually a really pretty good modeling of the cosine function with a polynomial of degree 4 in the vicinity of pi over 4. So you say, so what? Well, polynomials, as you may or may not know, are much, 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 much easier for machines to deal with than are transcendental functions. So in fact, I believe the programming of your TI-89s and even your TI-84s and so on actually have within them probably I don't know what degree, but a polynomial of a high degree that exceeds the error on your calculator, like 13 decimals, when used to approximate the transcendental functions. So yeah, your calculators are programmed with the Taylor polynomials rather than with what you think might be all these interesting values of cosine and sine and e to the x and so on. All right. So I think it's cool. Therefore, you should too. Okay, so determine the Maclaurin polynomial of degree 3 that approximates e to the x. All right, so once again, write your Taylor polynomial. Polynomial of degree 3 is equal to the function value at the point plus the derivative at the point times x minus a, that linear term, that point slope form for the equation y, plus the second derivative at a over 2 factorial times x minus a squared, plus the third derivative at a over 3 factorial times x minus a cubed. Okay, so what we need to do is determine, move this down for a second here, for e to the x, right? We need the Maclaurin polynomial again that tells you that we are approximating around x equals 0. Okay, so a is equal to 0 when we're talking Maclaurin polynomials. So we know the function is e to the x, so the derivative is e to the x. The second derivative is e to the x. Oh gosh, it's so nice. The third derivative is e to the x. And when x equals 0, we have 1, 1, 1, and 1. Could you ask for something prettier? I think not. So the third degree Taylor polynomial that models the e to the x function is 1 plus 1 x plus 1/2 x squared plus 1 over 3 factorial x cubed, or just 1 plus x squared over 2 factorial plus x cubed over 3 factorial. And you can really see, do we need to, we don't need to go much farther, but the next term is going to be x to the 4th over 4 factorial, x to the 5th over 5 factorial, and so on. It's just too cool. Okay? Well, take out your graphing calculators. This one you guys can do with me. Okay? Clear out what you got for those things. Enter in e to the x. Second, there, e to the x. And then 1 plus x divided by 2 plus x, oops, gotta do x squared divided by 2. There, that gives you time to catch up. X squared divided by 2 plus x cubed divided by 3. Not the nicest way to write it, but I think it'll still be understood. And then, let's see, what window did we have? We had a trig window, so we'll change that. Like -3 to 10. Should be good. Scale it by 1s. We don't really need a y min much below the x-axis. And then y max will go to 10 should be good. We'll take a look at that. Here comes e to the x, and here comes our polynomial of degree 3. Let's change our window, but look how cool that is. Even just that. That is too neat. We'll change our window a little bit. We don't need so many big x's. I guess we'll just go to 5 maybe, but let's take it up a little bit higher on the y's. Let's see, e to the 5th, 3 to the 5th. Let's go to 80. So there's the e to the x function. And in the vicinity of 0, I guess we're looking around 0, so that's pretty good. That is pretty good. That's too cool. Another way to look at these, I don't know if you're familiar with the Wolfram Alpha site. Brilliant math site. Unbelievable. You take a look at that. Earlier I did put in e to the x, and you just basically type whatever you want here. I wrote e to the x Maclaurin polynomial. Okay? It gives what's called the series expansion, which can be written, and you'll be doing this a bunch later. It can be written, set that down, I guess, and scroll down. The most common series way to write it is the sum k running from 0 to infinity of x to the k over k factorial. Does that work? For what we have? X to the 0 over 0 factorial plus x to the first over 1 factorial plus x to the second over 2 factorial plus x to the third over 3 factorial. And look at, this is the line. This is the, excuse me, this is, would be the quadratic, and this would be the cubic. I should write x cubed. But. Okay, so you see that as we increase the power on our Taylor polynomial, we increase how well it fits. Okay? I think I have one more. I think you guys should do that one. Find the fourth degree Taylor polynomial that approximates f of x equal to ln of x around x equals 1. All right, and then check. Graph it. Graph both the natural log function and your Taylor polynomial. They should look pretty darn close. So that concludes this lesson. I hope you guys followed things. You know, I mean, I think you can rewind this, replay it, and so on. Good luck. Your assignment is the circled exercises on the Taylor polynomial sheet. And I will see you soon.